Well, expansion and contraction can really wreak havoc on PV systems due to the extreme temperature changes they're subject to, and it's a consideration and concern for electrical systems in general. So what are the issues that we need to be concerned about in regards to expansion, contraction, and deflection? Well, it starts off based on those extreme temperature swings that I mentioned. Conductors or conduit that are on rooftops or exterior walls exposed to sunlight are going to expand and contract in regards to temperature changes at different rates than those on the inside of a building or those that are underground, or different compared to other materials that are exposed to the same temperature changes. Now, I want to think about the fact that the roof itself has an extreme temperature variation, right? From the coldest day in winter to the brightest, sunniest day in the summer. It is not unheard of for areas to have 100-degree annual swing, right? It can be pretty extreme. That stuff's all going to be exposed to that. We know that materials change, they expand and contract in regards to those temperature changes, and the differences between them, it can really cause some problems that we want to try and avoid as best as we can. So with wiring, pay attention to our wire bending radius. If we bend wires really tightly or we don't give them any slack that they can take up as they move, that can cause them to be damaged or to put pressure on the terminations where they're connected, possibly resulting in issues there as well. You'll really want to pay attention to sharp edges. Sharp edges, racking is one that I think of all the time when we have our wiring behind our PV arrays. Other sharp edges that we want to be aware of, things like hardware, screws, and things maybe in enclosures. Route your wires accordingly. And then we can always allow for extra movement by using junction boxes or pull boxes at strategic locations so that we can take up some of that movement and allow the wires and the conduits they're in to have the ability to move a little bit without damaging the wires. Conduit, in particular, is required to have expansion fittings. This is in section 300.7b. Or you have to use flexible conduit that allows for deflection. They recognize stuff is going to change in length. It's going to move a little bit. We need to be able to deal with that. Now, we'll look at some expansion fittings here in a minute, but we also want to think about the fact that some buildings, commercial buildings, have expansion fittings built into the building itself because, well, it's subject to expansion and contraction too. If I'm running a conduit across a building and crossing an expansion joint of the building, I probably need to have an expansion joint in that conduit too. Or if the building moves and the conduit's attached to the building, what's going to happen to the conduit? It's going to be subject to damage. We also want to think about allowing parts of our wiring systems to, making air quotes, float. Float. We don't want to bolt something down, and if it has expansion fittings in it, it's bolted into place, and now this expansion fitting can't move. It can't move. So we'll look at some examples here in a minute. Here's some examples of problems, things gone wrong with expansion and contraction. Let's start on the bottom. We've got a PVC conduit that pulled right out of this box that it was glued into. Maybe they didn't do a great job of gluing it, but I guarantee you that the expansion and contraction of this just pulled it right out of there. Here we've got some flex. That's good to allow for deflection, but we didn't have enough. It looks like this box, I'm pretty sure it used to be nice squared up here, and it got pushed this way and pushed that way, and now it's, it's not that it just looks bad and weird. It's possibly putting stress on the wires here. It's probably trying to open up this connection here. Eventually, over the years, it's going to lead to failure. Here we've got some other PVC on the roof, no expansion fitting. As we'll see when we look at some numbers, PVC changes a lot in regards to temperature change. This thing's all buckled and all over the place. Now it does have these curbs here that are used to hold down the conduit, and that gives it the ability to float. It can freely move through there. It's not clamped into place, but since we didn't give it an expansion fitting to take up that movement, it's still kind of got all wonky looking. Right, over time, this keeps moving. It might fall off of here. Probably one of these ends is going to pull out like that did, and we're going to see likely damage to the wires inside, which can lead to faults, failures, and fires. So bad stuff. Don't want to go there. Okay, so expansion and deflection fittings are addressed in sections 300.7b, 352.44, and 300.5j. The requirements here are that we have to compensate for thermal expansion, contraction, and deflection using these particular kinds of fittings. So what are these things? Well, here, first off, let's look at another bad example. See the conduit here coming up from grade, totally just pushed up, broke through into that box, very likely causing damage to the wires that are inside of it. Expansion fittings, and we'll see other images, maybe these aren't the greatest ones, but do you see the kind of the bulb or bulge in the conduit here? What that is it's a conduit inside of a conduit, and it's made so that it can slide inside. One part slides inside of the other one so that it allows for movement to happen. The fitting takes up and absorbs that movement and also has some reserve in there so that it can let some out as needed to compensate for contraction as well. Here we'll see a better photo later. These are expansion fittings on metal raceways, and we'll see those much closer up here in just a bit. So required when movement in a straight run between fixed points is greater than or equal to 1/4 of an inch. So that's not a whole lot of movement, is it? Well, when you think about how much a conduit fits into a fitting, that's not a whole lot of depth either. For a big conduit, it might be, maybe up to an inch, maybe a little bit more. For smaller conduits, it's not in there that far. So we don't want it to be able to pull out of there. So 1/4 inch is the minimum at which we need an expansion fitting in a straight run between fixed points. That's important to keep in mind. Fixed points, those meaning things that are not going to move. Now, they might move if the conduit expands enough. It might push a box like we saw on that earlier slide. The straight run is also a big part of it because when it's a straight run, well, that's our line. It can't really, there's nothing to take up anything. It's going to put pressure on the connections to those fixed points at the end. If, however, I have a run of conduit and it's got a bend in it, a 90 and then another 90, and then it continues on straight again, that bend is allowing it to take up some of that flex. Right? The bend itself can act as a means to absorb that expansion or contraction. So this is, again, straight runs between fixed points, or where conduit is buried and subject to movement from frost or settling. So this is another application we see for these all the time. That's what's going on here, right? We've got conduits coming out of the ground. We could get frost heave and movement, which could tear them out of the bottom of these wiring cabinets that the inverter is going to sit on eventually. So we've got expansion fittings on every one of these conduits so that we don't have the damage that occurs. Could be damage to the enclosure, could open up the conduit, and that can result in damage to the wiring inside. So that's the goal here, really. It's either straight run between fixed points or when subject to movement from frost or settling. So that frost or settling is a little tougher. It depends on where you are and how the system's laid out. We'll look at calculations for that first one and figuring out the movement because that's much less subjective. Here's an example. And on our example, we've got a couple of more examples of bad, right? Now, these may have never been made up appropriately to begin with, these connections, but either way, they're definitely failing now. And that's probably due to the thermal movement that's occurred over time. So here's a scenario. We've got an annual temperature change of 100 degrees Fahrenheit. 100 degrees F. So from our low temperature in the winter to our high temperature in the summer, realizing that, hey, that conduit on the roof that's in the direct sun probably is hotter than the air temperature. So maybe we want to think about that and take that into account for our total temperature change. The 50-foot length, that's again, in this example, we're assuming that is a straight run between fixed points. So let's look at both PVC and metallic examples. PVC changes a lot more with temperature than steel or other types of metal conduit does. But those, steel and PVC are probably the two that we see most often. So we get our expansion and contraction value from table 352.44. This is about PVC conduit, and it has a table that gives us change per 100 feet based on a temperature change. So with our 100 degree F annual temperature change, I see that a 100-foot length of conduit is going to change 4.06 inches. That's a lot of movement. 4 inches? I mean, that'll pull out of multiple fittings. We'll have multiple failures if we have allowed that much movement to occur. Table 352.44 also says, hey, steel only changes like 20% as much. 20% as much, right? So we're talking, in this case, like 0.8 inches for 100 feet of steel conduit subject to the same 100-degree temperature swing. Okay, but in our example, we don't have 100 feet. We got 50 feet, so we need to do a ratio. Here it's simple. It's half, right? But we could just do whatever our actual distance was divided by 100 and then get that multiplier to figure out what the actual change would be. Here, our PVC being about half of that 4.06 inches, around 2 inches of change. What do we say? Expansion fitting if the change is greater than a quarter inch. Okay, need one. Yeah, gonna have an expansion fitting for sure. What about steel? 20% change relative to the amount that PVC is going to change or expand and contract. So in this case, well, 20%, 2 inches of 20% is 0.4 inches. That's more than our 0.25 quarter inch. So we would need an expansion fitting on that 50 feet of steel conduit as well. So either way, expansion fitting's gonna be required in both of these cases, regardless of the material because of the temperature change and that overall length. So the math is pretty easy to do. You'll find in a lot of cases, any significant length of conduit on a roof is going to need expansion fittings. And of course, this is in addition to the consideration for coming out of grade and frost heave and settling that we talked about earlier. Okay, here's a couple of better close-up pictures of steel conduit expansion fittings. We always want to follow the installation instructions. I know you're probably going to guess what? If you're not tired of me saying that yet, you probably will be eventually, because it's true. You got to read the instructions. How do I set this thing when I first install it? It probably depends on how warm it is when you first install it, right? If you set it for hot temperatures and it's cold, when it gets hotter, it's not going to be able to do its job right. It's already going to be way too expanded or way too contracted. So we want to follow the instructions so that we get that thing set right to begin with. That's true for both metal expansion fittings as well as PVC expansion fittings. For metal fittings, the big consideration we need to keep in mind is that, hey, this is a metal raceway. It's going to need to be grounded. It needs to be connected to the equipment grounding system. The expansion fitting that allows movement, well, it kind of breaks the continuity, the electrical continuity of that raceway. So there's two ways to deal with that. And we've got both examples shown here. Internal or external bonding jumpers. So an internal bonding jumper, in this one you can't see it, it's built in. There's some kind of connection between the two sides that has enough slack in it so that as the fitting moves, as it opens up here and then closes back up again, that connection maintains continuity across it. The other method, where we don't have an internal bonding jumper, is a field-installed external bonding jumper. So here it is. We've got a connection to the conduit on either side, and there's a strap that also has some flex in it to allow for that expansion and contraction to occur. Again, it's going to depend on the particular fitting you're using. Follow the instructions. What about PVC? Well, PVC conduit's not conductive. There's no need to have bonding across it, of course. But we do want to make sure we install it right at the right setting based on the time and temperature we're putting it in. Okay, up next, we're going to get a little more PV specific, talk about PV system wiring methods. Catch you there soon.